Hello friends, welcome back to my YouTube channel. I hope you all are fine. I hope you all are watching my videos. So today I'm continuing my discussion on simple distillation. In my earlier few videos on simple distillation, I have discussed how to derive the governing equation for simple distillation, which is Raleigh's equation. Then I discussed one numerical, how to solve it. In that numerical, I discussed how to solve the Raleigh's equation graphically. Then, in my previous video, I discussed how to solve it analytically. And today, I'll be discussing the same numerical, but this time, I will tell you how to solve it by using a numerical method. Okay? So, this is part 14 of my discussion on distillation. So I'll be discussing a numerical based on simple distillation, and this time we will learn how to solve the Raleigh's equation by using a numerical method. Okay, again, in my previous two videos I had considered or I have discussed one numerical. Same numerical I'll be discussing today, but here we will learn how to solve the Raleigh's equation by using a numerical method. Okay, so let us start the discussion. For those of you who have not yet seen my videos, my earlier videos on simple distillation and other aspects of distillation, I am giving links to those videos in the description section. Okay, so let us first. So this is numerical number 3. Uh, numerical number 3. So in numerical 1, I have discussed how to solve it graphically. Then in 2, I have discussed how to solve the Raleigh's equation analytically, and now I'll be discussing how to solve it graphically. Okay, so let us first understand the statement. The statement is you have 120 moles of benzene and toluene solution containing 45% mole of benzene. It is subjected to a differential distillation at 1 atmosphere pressure. At the end of the operation, the composition of benzene in the residue is 29% mole. Calculate the total moles of mixture distilled. In this case, benzene is more volatile component and the average value of relative volatility is 2.16. Okay, so now let us first, as usual, note down the given things. What information is given to us? First, you have the feed solution. What is the feed solution? It is a solution of benzene and toluene. Let us call benzene as A and then toluene as B. Then quantity of feed solution is given to us. It is 120 moles. Benzene is the more volatile component. That is, benzene is having lower boiling point than toluene at the same pressure, or benzene has higher vapor pressure. Benzene has a higher vapor pressure at the same temperature. Okay, so from all this, the other information that is given to us is the feed is containing 45% mole of benzene in it. Okay, so from this we can note down F as 120 moles and XF as 0.45. Since it is containing 45% mole of benzene, mole fraction will be the percentage divided by 100, that is XF is equal to 0.45. Okay, then you have what is the process? The process is the feed solution is to be differentially distilled, so we have to use differential distillation or simple distillation to separate the components. The pressure, this operation is carried out at a pressure of 1 atmosphere, and at the end of this operation the residue is to contain 29% mole of benzene. So from this we can note down P as 1 atmosphere, total pressure is 1 atmosphere, and then we can note down XW, that is mole fraction of benzene, mole fraction of more volatile component in the residue, which we denote as XW. XW is 0.29. Okay, then you have, is any other parameter given to us? Yes, it is the relative volatility. The relative volatility is given to us, it is 2.16, so we denote it by alpha AB. This is 2.16. And what is the objective? The objective is to find out the total moles of the feed solution that gets distilled. That is, we are supposed to find out D. We are supposed to find out D. Okay. So now we have noted all the given things. Now we know what is our objective. Now let us start solving it. Okay. So now let us know the solution. So this will be numerical number 3. What is the approach? How are we going to solve it? Earlier uh, uh, we have solved it graphically, then analytically, and now let us know the new approach. The new approach is we are going to get D by using the following equation. F is equal to D plus W, which is the steady state material balance that we can write for simple distillation. Then F is given and W will be calculated, and it will be calculated by using Rayleigh's equation. What is the Rayleigh's equation? Rayleigh's equation is ln of F by W is equal to integration from xw to xf dx upon y minus x. Now the integral on the right hand side of this equation we are going to solve by using a numerical method. Which numerical method? There are multiple options, so I have chosen this one. I'll be using trapezoidal rule to solve this integral. What is the method? For example, let us understand the rule. So if you have this integral, I is equal to integration from a to b f of x dx, that is, we are supposed to integrate a function of x, which we are denoting as f of x. So integration from lower limit of a to the upper limit of b of the function f of x dx. Okay, so what is f of x? As I said, this is a continuous function on the interval a to b. So on the interval a to b, f of x is a continuous function. Okay, so let us understand. Let us move further. Okay, so let me first. This is numerical number 3. The integral on the RHS is solved by using a numerical method. As I said, the numerical method is the trapezoidal rule. So you have for this integral integration of f of x dx a to b, f of x is a continuous function on the interval a to b. Now the interval, what is the approach? What approach is used in with trapezoidal rule? Let me first tell you. So you have the interval from a to b. The interval is from a to b, and we will be have interval from a to b. Now what is the approach? So this interval, it is divided into sub intervals. Okay, so you can say that before you start at a, and then your objective is to reach B. But with this method, with trapezoidal rule, you'll be doing it like this. So you'll be starting at A, reaching one destination, then the other destination, then the third one, and finally you'll be reaching B. Okay, so that's why I'm saying the interval A to B is divided into subintervals. How many subintervals? Let us say that n subintervals. Let us say that the interval is divided into n subintervals. N is a number, positive real number. Okay, so if that is the case, then you can find out width of each interval. So the task is like, say, let me tell you once again. So you have A, you are supposed to go to B, and you have this distance, and now you are dividing it into small distances. And now we are talking about length of each small distance. So length of each subinterval. Okay, so if you are dividing B minus A, this particular interval, into n subintervals, then how do you get the width of each subinterval? So it will be simply B minus A upon n. Let us denote it as delta x. So delta x is equal to B minus A upon n. Okay. So A, we start at A. So let A be x0. A be x0. So next value for A will be x0 plus delta x. The third value will be x0 plus 2 delta x, then x0 plus 3 delta x, and the final value will be x0 plus n into delta x. Why n? Because we have divided the interval into n subintervals. So x0 plus n into delta x, and that will be the final value, that is B. Okay. So the other way of writing it is like this. See, A is x0, x1 is x0 plus delta x, x2 is x0 plus 2 delta x, or you can also write it like this. Say you have x0, that is A. Okay, so next value of x will be x0 plus delta x. Okay, and then the third value, that is x2, will be x0 plus 2 delta x, or I can also write it like this: x0 plus delta x plus delta x. So that is 2 delta x is delta x plus delta x plus, but x0 plus delta x is x1, so it can be written as x1 plus delta x. Are you understanding it? So similarly, you have x2, x3, and then finally you have xn, which is nothing but equal to b. Okay, so in trapezoidal rule, the given interval over which any function is to be integrated is divided into number of subintervals. So if you are dividing it in n subintervals, then the width of each subinterval will be given by this equation, and every time you will have to add the length width of the interval and then reach the upper limit for integration. Okay, so with this understanding, the formula which we can use as per trapezoidal rule for finding out the integral is integration from a to b f of x dx, that is equal to delta x by 2 into function evaluated at x0 plus 2 into function evaluated at x1 plus 2 into function evaluated at x2 plus 2 into function evaluated at x3 plus dash 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 plus the second last term is 2 into function evaluated at x n minus 1 and the last term is function evaluated at xn. Okay, when function is evaluated at x0 and then function is evaluated at xn, this will be the last first and last terms in this formula, and the remaining terms lying between these two will be multiplied with 2. So you remember this concept. Okay, so we are going to use this method to solve the integral. Okay, so after understanding the method, now let us note down first what are the steps involved in the solution. The steps involved, the first step is we will be solving the integral numerically, and we are going to use trapezoidal rule for that. Then after getting the integral, we will be using Rayleigh's equation to get W, and then finally we will be using total material balance to get D. 3 steps. So first get the integral. What is the integral? xw to xf and dx upon y minus x, and we are going to do it, or we are going to solve it numerically this time. And then we will be using Rayleigh's equation. What is Rayleigh's equation? ln of f by w is equal to this integral. So in this step we are going to get w, and finally we will be getting w by using the total material balance. Total material balance is f is equal to d plus w. Okay, so in this way we will be getting the final answer. Okay, so let us follow the first step. Let us go step by step. First step is we are supposed to solve the integral numerically. So let us do that. So I just told you how we are going to do that. We are going to use trapezoidal rule for solving the integral. Okay. Now the integral is I is equal to xw, integration from xw to xf dx upon y minus x. First we will have to have equation in terms of x. So for that we need to replace y, or we need to use equation for y in terms of x. And what is the equation? The equation is y is equal to alpha abx divided by 1 plus alpha ab minus 1 into x. Alpha ab is given to us, it is 2.16. So if you use it, it will be y is equal to 2.16x divided by 1 plus 2.16 minus 1 into x. That is y is equal to 2.16x plus 2.16 minus 1 is 1.16x. So you have y is equal to 2.16x divided by 1 plus 1.6x. Okay. Further, again this is numerical number 3. So you have let us solve the integral. We are solving the integral numerically. Previously we had got this I is integration from xw to xf dx upon y minus x, and we have one equation for y, which is 2.16x divided by 1 plus 1.16x. So if you replace it in the integral, so using the equation for y in the integral, you get I is equal to integration from xw to xf dx upon 2.16x divided by 1 plus 1.16x minus x. Okay, that is, if you simplify it, you can just get this. I is equal to integration from xw to xf dx upon 2.16x minus 1 plus 1.16x into x divided by 1 plus 1.16 into x. That is, again, some more simplification is done. So this 1 plus 1.16x dx divided by 2.16x minus x minus 1.16x square, which gives us another form, integration from xw to xf 1 plus 1.16x dx divided by 2.16x minus x minus 1.16x square, that is xw to xf, integration from xw to xf 1 plus 1.16x dx divided by 1.16x minus 1.16x square. Again, you can go one step further where you can take 1.16 common, so you have I is equal to integration from xw to xf 1 plus 1.16x dx divided by 1.16x into 1 minus x. So in this step, in the denominator, we have taken 1.16 as a common term. Okay, let us move further. So we have this equation, integration from xw to xf 1 plus 1.16x dx divided by 1.16x into 1 minus x. Now the limits are xw is 0.29 and xf is 0.45. That is, the lower limit is 0.29 and upper limit is 0.45. So it is integration from 0.29 to 0.45, 1 plus 1.16x dx divided by 1.16x into 1 minus x. Now we are going to divide the interval xw to xf into 10 subintervals. Again, I have decided to use 10 subintervals. You can use some another value for that, no problem. So therefore, the width of one subinterval will be delta x is equal to upper limit minus lower limit divided by number of subintervals. That is 0.45 minus 0.29 divided by 10, which comes out to be 0.016. Okay, so further, you have this, we have this integration. Integration from 0.29 to 0.45, 1 plus 1.16x divided by 1.16x into 1 minus x dx, and the subinterval is, length of subinterval is 0.016. Now the function you have in this case, the function is, we are supposed to integrate this function. What is this function? 1 plus 1.16x divided by 1.16x into 1 minus x. Now our task is, we are going to evaluate this function at every subinterval, which is required for using the trapezoidal rule. Okay, so let us move further. So you have, we'll start with x is equal to x0, and then the next value will be x0 plus delta x, that is x1 is x0 plus delta x, x2 is x1 plus delta x, and so on. We are going to get the function at each of this subinterval. Okay, so let us do it. So you have the function 1 plus 1.16x divided by 1.16x into 1 minus x. Now the function is evaluated at every subinterval. Let us start at the first, at the beginning, where value of x is x0, which is nothing but xw, that is 0.29. So you just have to use x0 in the function, so it will be f of x0 is equal to 1 plus 1.16x0 divided by 1.16 into x0, 1.16 into x0 into 1 minus x0, that is equal to 1 plus 1.16 into 0.29. I'm using value of x0, and I get the value for the function as 5.60. Similarly, it will be evaluated at x1. x1 is x0 plus delta x, that is 0.29 plus 0.016, which comes out to be 0.31. So we are going to put x is equal to 0.31 in the function. So that is f of x1 is 1 plus 1.16 into x1 divided by 1.16 into x1 into 1 minus x1, that is 1 plus 1.16 into 0.31 divided by 1.16 into 0.31 into 1 minus 0.31, which comes out to be 5.50. Similarly, for each subinterval we are going to evaluate the function, because we need that in the formula. Okay. So accordingly, I have done calculations for the remaining subintervals. So for various values of x, you get these values of function. Now we will be using the formula according to the trapezoidal rule. So integral will be given as integration from 0 0.29 to 0.45 is equal to 1 plus 1.16x divided by 1.16x into 1 minus x dx. In this case, where this interval is divided into 10 subintervals, the formula will be like this. It will be delta x by 2 into f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus 2 f of x4 plus 2 f of x5 plus 2 f of x6 plus 2 f of x7 plus 2 f of x8, 2 plus 2 f of x9, and the last term will be f of x10. Okay, so we have evaluated. So we have x0, x1, x2, x3, x4, x5, x6, so on and so forth. The last value is x10. Okay, so if you use those values, if you use the values of function, I'll be getting the integration from 0.29 to 0.45 plus of 1 plus 1.16x divided by 1.16x into 1 minus x dx, that is equal to delta x is 0.016, so it will be 0.016 divided by 2, 5.60. Now we are using the values of function at various x, so it is 5.60 plus 2 into 5.50 plus 2 into 5.42 plus 2 into 5.36 plus 2 into 5.32 plus 2 into 5.29 plus 2 into 5.27 plus 2 into 5.26 plus 2 into 5.26. You have the function has two values, 5.26 plus 2 into 5.28, and last value is 5.30. Okay, now simply you have to get the value. So if you solve it, you'll be getting the function as, so after using the formula, the integral value of the integration from xw to xf dx upon y minus x, which is integration from 0.29 to 0.45 of 1 plus 1.16x divided by 1.16x into 1 minus x dx, that comes out to be 0.85. You can just watch my previous two videos and compare the values, what value we got if we solve the integral analytically, and then what is the value that you get if you solve it graphically. You can compare. Now the Raleigh's equation is, we got it, we are going to use it to get w. So it is integration from xw to xf dx upon y minus x, that is equal to ln of f by w. So now we have got the value of the integral, it is 0.85. So it is ln of f by w is equal to 0.85. F is given to us, it is 120 moles. So that will be ln of 120 by w is equal to 0.85. That is 120 by w is equal to e raised to 0.85. That is 120 by w is equal to 2.35. E raised to 0.85 is 2.35. And then 120 by 2.35 is w. So that gives us w as 51.06 moles. Again, you can compare the value of w, this value, with the value that we got by using other methods. Okay, then the total material balance, in order to get d, f is d plus w. So that is 120 is equal to d plus 51.06. That is d is equal to 120 minus 51.06. That is d comes out to be 68.94 moles, and that is the final answer. Therefore, the total moles of the feed solution that gets distilled is, they are 68.94. Okay. So with this, we get the final answer, and I complete my discussion for this video. I hope you have understood how it is to be solved. You can, in place of trapezoidal rule, you can use any Simpson's rule for solving the integral, and you can check for yourself whether you are getting the same answer or same answer. You can check for yourself. Okay. So for now, thank you for being with me. Thanks for watching my videos. You please subscribe to my channel. You tell your friends to subscribe to my channel, and be with me in my future videos to know more aspects of distillation. Okay. So for now, it's bye bye. Have a nice day, and thank you for watching my video.